Okay, everyone. Good morning once again. Didn't get it yesterday. There's a new tutorial sheet of questions for my half. So if you didn't get it yesterday, you can collect one of those on your way out after this lecture. I'll leave it down here. So these questions are on series, which we started last week and continued yesterday. Okay. Now, I spent a fair bit of time yesterday reviewing the introduction to series, the two starting examples we looked at. So I'm not going to repeat myself going over those again. If you missed either yesterday's lecture or last week, do check out the recording, the YouTube recording, which is available off the review page. So we'll go straight back into it, and we were about to prove Theorem 2.3, which is the general term test. Now in this section, we have a whole bunch of convergence tests, which is a collection of tools that you can use to judge the convergence or divergence of certain series. None of the tools is perfect. They each have kind of partial performance. Sometimes they give you a conclusion and you try to apply them to a certain series. Sometimes they don't. That's what makes the subject interesting, but there is no one simple answer to the whole thing. So the general term test is a basic test that every series has to pass in order to have a chance of being convergent. So it comes in two versions, two equivalent versions, which are actually contrapositives of each other. So it's a nice example of a pair of contrapositive statements, which Saeed has been telling you about in the logic. So the first way of saying it is that if the limit of the terms is non-zero, as n goes to infinity, then that implies the series of those terms diverges. Okay. And that kind of makes sense. You can kind of appreciate that because if the things you're adding up are not disappearing, meaning converging to zero, then the size of the sum that you're adding up is just going to grow and grow and grow if they're always positive. Or if they're positive and negative, it's going to grow and sometimes shrink a bit and grow and sometimes shrink a bit. So it's not going to be settling down to any limiting value for the sum. The terms, step size that each partial sum changes by at each stage, those step sizes are not convergent to zero. So the contrapositive of this is that if the series converges, that implies that the limit of the terms as n goes to infinity is zero. You can see, you can appreciate there, I hope, how they are contrapositives of each other. The first one is the structure of A implies B, and the bottom one is the structure not B implies not A. And the warning I gave you yesterday is be careful with the directions of these arrows. If you reverse the direction of the implication, it's not true. Okay? So you'll run into trouble and you'll make mistakes if you assume that the implication arrow goes the other way. Knowing that the limit of terms is zero is not enough to know that the series converges. A classic example of that is the harmonic series, whose terms do converge to zero, but the series still grows without any upper bound. So the harmonic series diverges. Okay, and we were about to start the proof of this yesterday, but I postponed it because I didn't want to rush it. So we're going to prove the second version. We don't need to prove them both because they're logically equivalent, so I'm just going to prove one of them. So we're going to assume that we've got a convergent series. and we are going to prove that its terms converge to 0. So we're going to let epsilon greater than 0 be given. Let's see if I can do this. Somewhere down the bottom, we've got to imply that for all n bigger than or equal to n, the absolute value of an is strictly less than epsilon. That's what it means for a sequence to converge to 0. Yeah. For some point, for every n bigger than or equal to capital N, it must be true that the terms are strictly less than epsilon, and that this n can be found for any positive value of epsilon. So our task here, we know what we're trying to prove. This is from the definition of convergence for sequence. So we've got to find this correct value for capital N based on the value of epsilon and based on the assumption that the series converges. So this will apply to the limit as n goes to infinity of an is equal to 0. So that will be the completion of our proof if we can get to that stage. Now, we notice, what do we notice? We notice that if we write, I'll stick to the notation in the book, if we write capital AK to denote the partial sums of this sequence, capital AK is the partial sum, just adding up the first k terms, then we can express an element an will be an will always be capital AN minus capital AN minus 1. Because AN is just step size. It's the term that you add on to one partial sum to generate the next one. Because if you've got a partial sum to k, you just add on the next term, ak plus 1, you get the next partial sum. That's how the partial sums work. And since the series converges, there exists some point, let's call it capital M, such that for all values of the index little m bigger than or equal to capital M, we have sorry, let's write this. Let's write the value of this sum as L. The distance between AM and L is strictly less than, I'm going to choose epsilon over 2. Draw a little diagram here to illustrate what we're talking about. Here is the L. Here's the interval around it of size of radius epsilon over 2. But when you produce an interval of radius epsilon over 2, that means the length of the whole interval is epsilon, isn't it? So there's epsilon over 2 each side of L. So the length of the whole interval is epsilon. And this is saying that all these partial sums an, they're always inside this interval for every value of little n bigger than or equal to capital N. And the term an is the difference between two subsequent partial sums. So for n bigger than or equal to capital N, my an's all live in here. Okay? For n bigger than or equal to capital N. So that means the term little an, because it's the difference between two partial sums, the most the difference between two of these partial sums can be is epsilon. Because they have to be inside this interval. So the furthest distance they can get away from each other is epsilon, because that's the length of the interval. Okay. So that means the size of these things is going to be strictly less than absolute. Okay. So this implies that the absolute value of, let's say, well, if n is bigger or equal to capital N, the absolute value of an plus 1 minus an will always be strictly less than epsilon. These things are always in this interval, centered on L of radius of sine number 2, then the difference between any two of them will always be strictly less than epsilon. But this is the element an plus 1. Okay? Because little an plus 1, that's the difference between these two partial sums. So if we just want to fix up with this n at the end, so we let capital N be n plus 1. All right. Yeah. There's just this odd, because you're talking about differences of neighboring partial sums, just the point has to move one further on. But it's the main idea is essentially contained in this diagram. If the series is convergent, that means the sequence of partial sums converges to something. So that means, given any epsilon, we can say after some point, the partial sums all live inside this interval, this small interval around the limit. But we've arranged it so that this small interval around the limit has total length epsilon. But the difference between any two consecutive partial sums is one of the terms of the series. So that means the terms of the series must all be strictly less than epsilon beyond this. Okay. So that says that the terms of the sequence, the terms of the series, the little an, converge to 0. Okay. So we proved that. We proved the general term test. So that's that gives us our first basic test that allows us to detect. Now, it doesn't detect convergence, it detects divergence some of the time. If you're shown a series and you can see that the terms of the series do not converge to 0, you know straight away the series diverges. Because we've just proved that if the series converges, the terms do converge. So if we see the terms not converging to 0, we know the series diverges. So the general term test is a tool that can detect divergence. Okay, moving on then to the geometric series test. So this is a much more practical kind of thing that gives you a formula so that you work things out. So this applies to geometric series. Geometric series is one of the form. Well, it's just where the terms look like a geometric sequence. So geometric series looks like this. It's the sum of all the terms a times r to the n minus 1, when n goes from 1 to infinity. So this series looks like a, some initial term a, the next term is ar, the next term is ar squared, the next term is ar cubed, and so on and so on. It's that infinite series. And the theorem is quite powerful. It tells the complete story about these series. It says if a is non-zero, then if A is non-zero, then this converges if and only if absolute value of R is strictly less than 1. So if the absolute value of R is not strictly less than 1, and A is non-zero, then the series diverges. And if it is strictly less than 1, in that case, not only do we know it converges, but we actually have a nice, simple formula that gives us the sum of the series. But the geometric series is almost unique amongst the convergence tests that it actually provides you the value of the series. Most of the other convergence tests do not give you a precise value of the sum of the series. Obtaining some precise values of the sum of the series is in general maybe not easy. But this is a really nice result in that it's the complete story really for all geometric series in terms of whether or not they converge and what the value of them is. Okay. So we can do this. First of all, we'll deal with the trivial case of what happens if A is 0. Well, if A is 0, it's really not a proper geometric series, really, but technically it still is. Then the sum of A R to the n minus 1 from n goes 1 to infinity. Well, if every term is this factor of 0, it means your infinite series is just 0 plus 0 plus 0 plus 0 plus 0 plus 0. That's obviously convergent. The partial sums are all equal to 0. The sequence of partial sums clearly converges, and it converges to 0. So we won't waste too much time on that. It's not really a proper geometric series, but technically it does fit the pattern. So now we can assume that in everything else we do, we'll assume that the A is not 0. Okay? So we've already dealt with the 0 case. One more case to deal, separate case to deal with. If R is equal to 1, then our series, again, it reduces, it's much simpler. If R is actually equal to 1, then these factors of R to some power, they don't make any difference at all, because it's always just 1 to some power. So there the series actually looks like A plus A plus A plus. So you're adding up an infinite number of A's. But we're now in the case that A is non-zero. So even if A is tiny, 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 still if you add up an infinite number of them, you can grow to any size whatsoever. So this is a clearly divergent series. It's just increasing by a fixed step size each time, and there's certainly non-zero step size. So it certainly diverges. This clearly diverges. So now, having dealt with that case, now we can assume that R is not equal to 1. And now we can give the general argument. So now we're going to be thinking about a geometric series, which is non-trivial. The A is not 0. So it isn't this trivial one. And also the R, the common ratio R, is not equal to 1. So it isn't, the step size is changing each time. Okay, and we do a little trick. We look at one of the partial sums. If we let Sk be the partial sum of one of these things, so the AR to the n minus 1. So this is going to look like A plus AR squared, all the way up as far as AR to the k minus 1. That's the last term of the partial sum. And if we multiply this by R, we think of RSK, well, that'll be equal to AR plus AR squared plus AR cubed, all the way up as far as AR to the K. Now those two series, just the partial sum SK and the partial sum multiplied by R, they look extremely similar. They're almost identical. These two terms are the same, these two terms are the same, that term and that term are the same all the time, and then this term here is the same as the penultimate one down here. So when you subtract them, you look at SK minus RSK, everything cancels except for this initial A up here and this final AR to the power K down there. All the other differences cancel. All the other parts of the difference are zero. Because each bit here has its counterpart down here, and you're subtracting the bottom series from, or the bottom sum from the top sum. And that implies factor the left-hand side, factor the right-hand side, and divide across, and we get a nice formula, very nice formula for SK. And you can also see why I dealt with the R equals 1 case separately above, because in the R equals 1 case, we wouldn't have been able to do this. You can't divide it. You can't divide by 0. So note that R is not equal to 1. We assumed it wasn't. Okay. So we get a really nice formula for the kth partial sum. And remember, the convergence of a series is the convergence of its sequence of partial sums. So here we have a nice, completely straightforward description of the partial sum, so we can judge the convergence of this thing. So we ask ourselves, does SK converge as a sequence? Does the sequence of partial sums converge as a sequence? Well, using our algebra of limits theorem for sequences, and this is good, we should always be on the lookout for like reusing our results, making use of the theory that we've gone to the trouble of proving. And we can do that here now. The limit of SK is the limit as k goes to infinity of a times 1 minus r to the k over 1 minus r. So that's a limit of a combination of constants, a, the 1, and the r, and this non-constant part, which is the r to the k, that's changing as k. So the algebra of limits theorem will tell us that this is the limit of this, if it exists, is going to be a times 1 minus the limit as k goes to infinity, r to the k, all over 1 minus r. So that's an important step. That's by the algebra of limits theorem for sequences. Okay, which we've already proved a number of weeks ago. A limit of a, because we proved a limit of a product was the product of the limits, a limit of a quotient is the quotient of the limits, a limit of a difference is the difference of the limits. Okay, we proved all that, and now we're able to use it. And so now we can judge the convergence straight away. We can say, note that if the absolute value of r is less than 1, then r to the k converges to 0 as k goes to 1. That makes sense, because if a number has absolute value smaller than 1, when you multiply it by itself, it will have even smaller absolute value. So as you raise it to higher and higher powers, the absolute value of it is getting smaller and smaller and smaller. It's converging to 0. But if r happens to be minus 1, or the absolute value of r is strictly bigger than 1, remember we've dealt with the r equals 1 case already. We don't need to deal with it again. If r is minus 1 or has absolute value strictly bigger than 1, then r to the k diverges as k goes to 1. If it's absolute value bigger than 1, when you multiply r by itself, you have even bigger absolute value. And that continues and continues and continues as you multiply, as you raise it to higher powers. If r happens to be -1, then r to the k just alternates between +1, -1, +1, +1, -1. So you're not converging. It's not blowing up in absolute value, but it's not converging. Okay, it's just oscillating between the two values, +1 and -1. So if absolute value of r is strictly less than 1, we have convergence. And we can say that the infinite sum of the geometric series, which by definition is the limit of the partial sums, that's going to be a over 1 minus r. It's the limit of r to the k is 0. Oops. So when absolute value of r is strictly less than 1, we do have convergence, and even better than that, we have a simple enough formula for the sum of the series using the a and the r that tells you what the sum of the series is. Okay, I'll show you a few examples of using that. But any questions about the proof of the argument? So it's good to spot a couple of things that work there. It's good to spot this part here. This is the definition of the sum of an infinite series at work. The sum of the infinite series is the limit of the sequence of partial sums. And it's also good to see reusing a tool from our theory about convergence of sequences. So that's important. Okay, so let's look at some examples. Well, the first example we could show is the one that was one of our introductory examples, which was a sum of powers of half. Half plus a quarter plus an eighth and so on. Well, this is an example of a geometric series. This is geometric with a equals a half, and in fact r equals a half as well. So the initial term is a half, and each time you're halving the previous term to get the next term. So it's convergent. And the sum of the series is given by the formula a over 1 minus r, so it's a half over 1 minus a half, so it's a half over half, so it's 1. And that confirms our argument before that when we're taking step of a half, and step of a quarter, and step of an eighth, I'm just gradually trying to cover the whole distance between my start point and get to the desk. I'm just stepping a half the remaining distance each time, so I get closer and closer to get to the desk, and in the limit of the limit never happens, but the limit of that process is the empty field. So this that kind of intuition type reasoning we gave for this series at the very beginning is now backed up completely by the use of the geometric series. We can get another example if we say go look at page 25. We look at some of the end of chapter exercises. See question 4 on these. Question 4, part 1, say. Question 4, part A. This question is basically investigate the sum of xn, where it's kind of given to you in a kind of an obfuscated way, a bit more complicated than need be. Okay, that's question 4a. Investigate the sum of this series where the term xn is equal to this. Now we recognize the fact that it's geometric because in the term, the only thing that changes is we get powers of these fixed constants. Okay? And the powers are n is the index of the series, so it all looks good. But we might want to, I mean, this, if we want to apply our theory and our formula, we need to see this. We need to determine the values of the two parameters, a and r. So we just need to kick this around a little bit until it's fitting into that pattern. So I'll take this 2/3, this quarter, and I'll reduce these exponents down to n minus 1 by taking out one of the halves, one of the 2/3. And then rather than it being, so then it's going to be a half to the n minus 1 multiplied by 2/3 to the n minus 1. But of course, the property of powers is that product of two powers to the same exponent is just the power of the product. So it's going to be a half times 2/3. So that's all going to simplify somewhat to 1 over, what's that? 1 over 18. All right. 1 over 18 times 1/3 to the n minus 1. So we see there what the a and the r is. The a is 1 over 18. The r is a third. So the third is clearly has absolute value strictly less than 1. So it is a convergent series, because that's what the criteria is. If the absolute value of r is strictly less than 1. Well, it certainly is. So sum of xn is convergent. And we can use the formula that says the sum of xn, and that equals 1 to infinity, is a over 1 minus r. So it's an 18th over 1 minus a third. So it's an 18th over 2/3. Just whatever it is, was it? Third goes away. 6th over 2, 12. If I made an arithmetic error, please. Did I? Yeah. You're confirming it's right? Yeah. Okay, so we probably both made it arithmetic. I have very little confidence in myself when I whiz through calculations like that. But I do. Okay. So you see how we can apply the geometric series in a certain way, and it's really, really nice that it does spit out a value at the end. It does tell you what the value is. But it is almost unique amongst the convergence tests in that it does that, because most of the others do not. Most of the others do not. So we'll end by looking at another one of the tests, which is the integral test. Yes. So there's a diagram that goes along with this. Now it's slightly, here in 2.5, it's slightly unfortunate in that we're talking about integrals, and we haven't formally covered them in the course yet. Saeed will be taking you through the integral calculus, the theory of integration, soon, or later on in the year. But you know, we do all have some previous exposure to the process of integration. So we will refer to it here. So here we're considering a series. Now maybe just a time to sketch out the idea behind this proof. And in the book, it's not done completely formally in the book, but it gets across the main idea. So we're considering a series of non-negative terms, positive terms, where there is a nice continuous function f with decreasing values, where the am is actually equal to the value of this function f at the value n of the index and then it basically says if the integral of this function from 1 to infinity exists and is finite, then our series converges. If the integral does not have a finite value, then our series diverges. Now, the proof of this, it isn't tackled incredibly formally in the notes, but the main idea comes down to a nice diagram. And unfortunately, when I was writing the text of the proof, I referred to the red bits and the blue bits in the diagram, but of course it's printed in black and white for you, so that's not much use. So I'll try and reproduce it here. We've got a pair of axes. That's not very red colors. Okay, so let's draw first of all, let's draw our function. So here is our decreasing function with positive values. Okay, that's our function f. Here, this is these are our values of n, 1, 2, 3, 4, 5, etc. And we're familiar with the idea that the integral from 1 to infinity of f of t dt is equal to the area beneath the curve. Okay? The area between the x-axis and the curve, between the limits of 1 and everywhere beneath the curve. Okay? This area. But the sum of the series is also associated to an area here as well. See, because A1, the quantity A1 is actually the area of that rectangle. Everybody knows the area of a rectangle is its width by its height. The rectangle is width 1 and height A1. Remember, because A1 is equal to F1. So that rectangle has area A1. This rectangle has area A2. This rectangle has area A3. That rectangle has area A4, and so on. Okay. The sum of the series corresponds to the area of the rectangles. Now, there's a strong relationship between the area of the curve and the area of the rectangles. They're almost the same. That's the observation. They're almost the same, but of course they're not quite the same because of these protrusions up here. Okay? So the sum of the series, you can say is equal to the integral of the function plus an extra bit, which we denote by gamma, Greek letter gamma. So gamma equals the sum of all these red protrusion bits, which all have this kind of shape. And we're summing over n. Okay, now what do we notice about the red protruding? Okay, you can see that from the picture. The area underneath the graph, or the area of the rectangles, is the area underneath the graph, plus the areas of those extra bits that poke out at the top. But what we notice about those extra bits that poke out at the top, they are seeming to get smaller. And there's a really nice, outrageous argument that says, actually, you can just slide them all to the left. So take all those rectangular bits and slide them all horizontally, parallel to the x-axis to the left. I say it's outrageous because it suddenly gives you it suddenly completes the proof. All these red extra bits, if you slide them to the left, they all fit into the first rectangle. Well, why is that? They're certainly all above the x-axis because the function is decreasing. The function never goes below the line, so there's never a bit of these protruding bits beneath the x-axis. And they never overlap because the function is decreasing. Should say, maybe up here, it should be strictly decreasing. The function is decreasing, so each red protrusion bit never overlaps with the one below it when you slide them horizontally to the left. Okay? So notice all the protrusions. All the protrusions can be translated to the left to fit into the first rectangle with no overlaps. What that means is the sum of all those protrusions is a convergent series. Technically, we're using the monotone convergence theorem here, because the sum of all the protrusions is bounded by the quantity A1, because the area of the first rectangle is A1, and all those protrusion areas fit inside it. So the sum of them all has to be less than A1. Okay? It must have a total area less than A1. And it's a increasing sequence, it's a sequence of positive terms, a series of positive terms. So the sequence of partial sums is an increasing sequence. It's bounded above by A1. The monotone convergence theorem tells us it must be convergent, and therefore it must have a value. So gamma, which is the infinite sum of all these protrusions, is convergent and has a finite value, which will be less than or equal to A1. In fact, it's less than or equal to A1. So that tells us then we return to this equation, and then the conclusion of the theorem comes from looking at this equation. Because it says the sum of the series is the integral plus a finite. So if the integral converges and has a finite value, then so does the sum. But if the integral does not converge and has an infinite value, so if there's an infinite area underneath the curve, well then the sum of the series is the integral plus a bit. So therefore the sum of the series has to be infinite as well. So because the two quantities, the integral and the series, because they differ by only a fixed finite amount, if one of them converges, so does the other. one of them diverges, so does the other. So the convergence of the sum of am and the integral of ft and t, the convergence of these are linked, and the conclusion follows. The theorem follows. Okay, it's spelled out, more or less, that argument. And as an exercise, I think it's talked about in the notes. Well, it's referred to slightly later on. I'll set this as an extra exercise for you. Use this integral test and some known integrals, standard known integrals that you will know about, to judge the convergence of any series that looks like this, the sum of 1 over n to the power a, where n goes from 1 to infinity. So the sum fixed. So how does the convergence of this thing depend on a? That's the question. So you want to get a conclusion that this converges for some a and diverges for other a. That's the kind of conclusion you're looking for, but you want a precise description of which a does it converge for, which a does it diverge for. So you can answer that question by using what you know about integration, about integrating functions that look like that, 1 over t to the power a, and the integral test. Okay, so that's like an extra exercise for you to be thinking about in the meantime. For the tutorials off the tutorial sheet, anything from, I think, questions 1 to 7 are you should be working on. Again, there probably won't be enough time in the tutorials to work through all of those questions, but I just want to give you loads of questions to do, plenty of questions to do to keep you busy outside of the classes. If you haven't got one of these tutorial sheets yet, there's a little pile of them here. Get one on your way out. And we'll finish there. Thanks for listening.